Alright, section 3.6 deals with logarithmic and exponential models. And you've done stuff in the past with models before. Models are just equations, but they're equations that are used in a way to model real-world situations. So we're going to talk about 5 of the most common logarithmic and exponential ones. A couple of them we'll look at examples for during this section, and a few others we'll just have a little bit of a discussion on without actually getting into the problems. Alright, there's 3 of the 5 that we're going to talk about are listed below. 2 of the more common ones for exponential are exponential growth model on the left side here, and exponential decay model, so growth and decay. A couple places for this might be population growth or germ growth or virus spreading, things like that. Exponential decay, again, population as elements break down in a lot of different situations like that. For the exponential growth, it's usually going to take on the general form y equals a times e raised to the bx power, and it's going to have a general shape like we've done already with some other exponential functions. Exponential decay, the only difference that you're going to see in the form of the equation is it's going to be the opposite of bx when we get up into the exponent. Otherwise, it's going to change and be reflected over the y-axis compared to what we had originally on the other side for exponential growth. So again, these are just general graphs that we're going to look at here. Steepness and curve and where they cross and shifts, everything else can change a little bit depending on the actual values for the problem you're working with. So again, these are just general shapes. Another one that we haven't worked with a whole lot in our class yet shows up a lot in statistics and probability, and it's called a Gaussian model. And the Gaussian model takes on this form: y equals a times e, and this entire part up here is the exponent for e. So negative x minus b all squared all over c. And again, we'll talk a little bit about this one, although we're not going to really focus on it until maybe later in the course. And this kind of takes on, like we said, it deals with a lot of statistics situations. When they talk about a normal curve, or in layman's terms, we talk about the bell curve, where if everything is normalized, a majority of the people are going to fall in the middle of the bell curve, with some smaller values to the far right and to the far left, away from what we would consider the average. So again, that would be the Gaussian model. A lot of times you'll see that in educational testing, where they're talking about test scores and IQs and so on. Where do you fall compared to the norm? They would fall under this model. So our other 2 types, one is a logistic growth model, and this might be one where a good representation nowadays might be if you're in a population area where all of a sudden it's kind of flat, and then for some reason a new business moves in the area, whatever, all of a sudden the population picks up in its rate, grows really fast. Well, that can't keep going forever, and eventually it hits a peak and kind of slows back and levels off again. That would be a situation for logistic growth, and this would be the form that we would use for that. And our 5th type, we've already dealt with a little bit in this chapter, is a logarithmic model, and we've got the 2 basic ones here, a common log and a natural log, and they're going to take on a form y equals a plus b times logarithm of x. And again, this would be a common log with a base 10, and this would be a natural log with a base e. And just like on the last screen, again, all 3 of these graphs are general shapes. They'll get more specific once we plug in our values and start solving our problems. Alright, now let's look at one situation where we can use one of these types of models. Alright, so here's the problem we're going to use, and we're going to look at exponential growth. And this is another place where you see exponential growth a lot of times is in terms of sale, especially when industries take off and things happen really, really fast. So here's what the problem is going to be. Billions of dollars are spent every year on advertising in the United States. Below is a chart showing ad spending in billions of dollars from 2007 through 2011. So again, you can see the table here. In 2007, there were $21.1 billion spent on advertising and so on over the course of these 5 years. Now, we're going to use an exponential model, like we said, an exponential growth model, and this is one that I'm not going to show on the video here, but in class we'll look at it. We're going to use a regression model. And you've done linear regression, you've done median lines in the past. This is another type of line of best fit type situation where it just happens to fit exponential, where again it's going to have that curve for growth. And when we look at it in the calculator, you'll actually see that curve taking place on the scatter plot. So we'll plug the values into our calculator. We'll have a column for years, we'll have a column for spending, and we'll come up with an equation that will fit this model very well. So we're going to use our exponential growth model of y equals ae raised to the bx. And again, I'm not going to show it here, but on the calculator, once we plug these values in and use the regression model, the formula that you see in the upper right here is what we came up with. So, a couple things that we have to do on this one. One of the questions that they wanted to ask down here, when would we predict that ad spending will reach $40 billion in the United States? So if we take a look at our formula here, the y is going to be our end amount, so that's where our 40 is going to go in terms of 40 billion, and then we're just going to set up our equation here. So we get 10.33 e raised to the 0.1022t, and again, since we're looking for when, that's our time, we've got everything set up here in nice shape because t is our only variable that we have left. So on this one, we're going to just start out fairly simple and go back to basic algebra here, and we want to isolate the e, since that's the part where the exponent has the variable we're trying to find. So we're just going to divide by 10.33 on both sides. Now, even though we've already rounded this down to 10.33, I'm still going to recommend that you leave this in this form. Don't divide and then round again. You start introducing more error into your prediction later on by doing that. So we're going to set this one up. This is going to cancel on the right side, so we're still going to be left with this fraction on the left. And on the right side, all we have left is our exponential. So e raised to the 0.1022 times t. So again, one thing that we can do is we can apply a natural log to both sides since this is base e. So on the left side, we're just going to get natural log of this fraction. And again, it's a little messy to keep writing it, but it's going to keep our answer a little more exact, I guess would be a good word for it. This side we're going to do natural log of e to the 0.1022t. So on the left side, nothing to simplify, we're just going to keep that. So our natural log of the fraction that we've been carrying along for a few steps now. Oops, let's clean that up a little bit. And on the right side, since this is base e, we can follow one of our properties, and it's going to leave us with our exponent as our simplification. Now one more step, just to get the t by itself, we're going to divide by our decimal here, 0.1022, and we're going to do that on both sides. So again, this side, pretty simple, just cancels out, and then we're just going to hit up the calculator to get our solution. So we're going to find the natural log of this fraction, Again, be careful to put that in parentheses in your calculator, because the calculator will mess it up for you. If you just do it without, it'll just do order of operations, and it'll actually just do natural log of 40, find that solution, and then it'll divide by 10.33. So put it in your calculator as you see it here, divide by 0.1022, and it's going to come out to be, or it should come out to be, approximately 13.25. So that's how many years it would be. And when you go back, and you'll know this in class, when we did this one, when we plugged everything in on the calculator, we actually let this be year 7, year 8, year 9, year 10, year 11. So when we get this, we know that sometime in 2013 is when we would predict. Again, technology here. Again, in the year 2013 would be our prediction based on our model of when we're going to cross the $40 billion threshold in advertising. So that's one method that we can look at here, and that's exponential growth.